Hello, my dear students. Welcome to IKSR chemistry classes. In this video, we will discuss Nephelauxetic effect and Racah parameter B. First of all, let us see what is interelectronic repulsion. Electron is negatively charged. It is a well-known fact. When an atom has more than one electron, there is electrostatic repulsion between similarly negatively charged electrons, which is called interelectronic repulsion. It is a well-known fact that electron is negatively charged, and if an atom contains two or more electrons, there is electrostatic repulsion between similarly negatively charged electrons, and it is called interelectronic repulsion. The magnitude of this interelectronic repulsion depends on following factors. First of all, the number of electrons. Greater the number of electrons in an atom, greater will be the interelectronic repulsion. Some other factors affecting interelectronic repulsion are also given here. The spin of electrons, the nature of orbital they occupy, and the distance between electrons. These last three factors will be discussed with the help of diagram on the next slide. Here, two electrons are closer to each other, and therefore there is greater interelectronic repulsion. But if the electrons are moved apart, that is, the distance between the electrons increased, there will be a smaller interelectronic repulsion. And if these two electrons have parallel spins, both have alpha spins, and if one of the electron has inverted spin, that is beta spin, and this has alpha spin, then there will be a smaller interelectronic repulsion. It means two electrons having opposite spins exert a smaller interelectronic repulsion, while two electrons with parallel spins produce greater interelectronic repulsion. In this diagram, two electrons are present in px and py atomic orbitals, and these two are closer to each other, and there is greater interelectronic repulsion. While if here two electrons are present in dxy and dx square minus y square atomic orbitals, these are the lobes of 1, 2, 3, 4 of dxy atomic orbital, while these 1, 2, 3 and 4 lobes are of dx square minus y square atomic orbitals. Here two electrons are at farther distance in comparison to here, and therefore there is a smaller interelectronic repulsion. These are the factors affecting interelectronic repulsion, and the most important of them is distance between them. As the distance between electrons increases, the interelectronic repulsion decreases. It has been found that the electron repulsion, that is interelectronic repulsion of the metal ion in a complex compound, is lower than that in corresponding free metal ion. It has been found experimentally that the interelectronic repulsion of the metal ion in a complex compound is lower than that in corresponding free metal ion. This effect is known as Nephelauxetic effect, which means cloud expanding effect. The interelectronic repulsion of the metal ion in a complex compound is lower than that in corresponding free metal ion, and this effect is known as Nephelauxetic effect, which has word meaning cloud expanding effect, and the term Nephelauxetic effect was first introduced by the Danish chemist C.K. Jorgensen. The Nephelauxetic effect is nothing but d electron cloud expansion effect. It means in Nephelauxetic effect, the d electron cloud of metal ion expands on the formation of complex compound. When a transition metal ion forms a complex compound, the effective size of d atomic orbitals of the metal ion containing the electrons increases. When a transition metal ion forms a complex compound, the effective size of d atomic orbitals of the metal ion which contains electrons increases. It means d electron cloud of the metal ion expands. D electron cloud of the metal ion expands on the formation of complex compound, and hence it is known as Nephelauxetic effect, which means cloud expanding effect. Here the cloud is d electron cloud because the valence electrons of transition metal ion are present in d atomic orbital. It results, the expansion of d electron cloud results in increase in interelectronic distance and decrease in interelectronic repulsion. When a transition metal ion forms complex compound, its d electron cloud expands. As a result, the distance between electron increases and the repulsion between electrons decreases. Diagrammatic representation: it is dx square minus y square atomic orbital of the transition metal ion which contains electrons, and when the transition metal ion forms complex compound, that is, ligands approach the transition metal ion during complex formation, the lobes, the size of this d atomic orbital increases. D atomic orbital expands when the ligands approach the transition metal ion forming complex compound, so that d atomic orbitals of the metal ion can overlap with the ligands more effectively. Here the size of d atomic orbitals has increased and therefore interelectronic distance increases and interelectronic repulsion decreases. Reason for Nephelauxetic effect: the orbitals of the metal ion take part in linear combination with the orbitals of ligands. During the formation of complex compound, the orbitals of the metal ion take part in linear combination with the orbitals of ligands, forming larger molecular orbitals, in which the electrons of the metal ion become more apart. Now the electrons can move in a larger space due to the formation of molecular orbital, and the increase in interelectronic distance results in decrease in interelectronic repulsion. When a transition metal ion forms complex compound, the atomic orbital of metal ion takes part in linear combination with the orbital of ligands, forming molecular orbitals of larger size, in which the electrons can move in a larger space and they become apart from one another. As a result, the interelectronic distance increases and interelectronic repulsion decreases. Racah interelectronic repulsion parameter B. The interelectronic repulsion of free metal ion is represented by Racah interelectronic repulsion parameter, which is also simply called Racah parameter. Please note it again that in free metal ion, the interelectronic repulsion is represented by Racah interelectronic repulsion parameter, which is also called simply Racah parameter. It is denoted by B and expressed in centimeter inverse. Greater the value of B, greater the value of Racah parameter B, greater will be interelectronic repulsion, and a smaller will be interelectronic distance. B is interelectronic repulsion parameter, and greater the value of B, greater will be interelectronic repulsion, and consequently a smaller will be the internuclear distance. Racah parameter B for some transition metal ions are given in the following table in centimeter inverse. These are Racah parameters B for di-positive transition metal ions. Vanadium 2 plus has Racah parameter 755 centimeter inverse, while vanadium triple plus has 861 centimeter inverse. You may note that the Racah parameter B is increasing in this direction and it also increases in this direction. It is 860 and it is 965. It is 917 and it is 1015. The Racah parameter B increases in this direction also and in this direction also. And the following conclusions can be drawn from the above table. On moving from left to right along a transition series, the value of B increases. For example, vanadium 2 plus, chromium 2 plus, manganese 2 plus, Fe 2 plus, and cobalt 2 plus, nickel 2 plus. On moving from left to right along this transition series, ionic radius decreases. As a result, interelectronic distance decreases. When the radius becomes smaller, the electrons come closer to one another, and the interelectronic distance decreases, which results in increase in interelectronic repulsion. On moving from left to right along the transition series, radius decreases, interelectronic distance decreases, interelectronic repulsion increases, and the value of B increases. As evident from the above table, it was increasing on moving downwards, but this has been written on the horizontal position here. The value of B for tri-positive metal ion is greater than its di-positive ion. We have already seen nickel 2 plus has a smaller value of B, while nickel triple plus has greater value of B. On moving from nickel 2 plus to nickel triple plus, the ionic radius decreases Greater the positive charge on an atom, a smaller will be its radius, and the decrease in ionic radius results in decrease in interelectronic distance, increase in interelectronic repulsion, and increase in the value of B. Ni triple plus has a smaller ionic radius than Ni 2 plus. Ionic radius decreases, interelectronic distance decreases, interelectronic repulsion increases, and the value of B increases. Attention! The interelectronic repulsion parameter of metal ion in a complex compound is represented by B dash, while in free metal ion it is represented by B. As discussed above, the value of B dash will be lower than B, that is, interelectronic repulsion parameter in complex compound is lower than that in free transition metal ion. Let us see it with an example. The value of B for free Ni2 plus ion is 1030 centimeter inverse. But in this complex NiF6 4 minus, the value of B, that is B dash, is equal to 843 centimeter inverse. The value of B in a complex compound is lower than that in free transition metal ion due to Nephelauxetic effect. Nephelauxetic ratio, which is also called Nephelauxetic parameter. The decrease in the interelectronic repulsion of metal ion on complexation is expressed in terms of Nephelauxetic ratio or Nephelauxetic parameter beta, which is given by the expression. Let us see it again. The decrease in the interelectronic repulsion of metal ion on complex formation is expressed in terms of Nephelauxetic ratio or Nephelauxetic parameter, which is denoted by beta and given by the following expression. Beta is equal to B dash divided by B. It means interelectronic repulsion parameter in complex compound and divided by interelectronic repulsion in free transition metal ion, where beta is Nephelauxetic ratio or Nephelauxetic parameter. B is interelectronic repulsion in free metal ion and B dash is interelectronic repulsion of metal ion in complex compound, as we have discussed earlier. Since B dash is smaller than B and we know that beta is equal to B dash by B, here B dash is smaller than B and therefore beta will be less than 1. The value of beta generally lies in the range 0.7 to 0.9. It means the interelectronic repulsion in metal ion decreases by 10 to 30% on complex formation. The interelectronic repulsion of metal ion decreases by 10 to 30% during complex formation. The value of B dash, that is interelectronic repulsion in complex compound, is determined from gaseous phase UV visible spectroscopy. As smaller the value of B dash, smaller will be beta. As the value of B dash decreases, the value of beta also decreases, and greater will be electron cloud expansion effect. As smaller the value of beta, greater will be electron cloud expansion effect. If the beta has value 0.7, the electron cloud expansion effect will be higher, and if the value of beta is 0.9, the electron cloud expansion effect will be lower, and if the value of beta is 1, there will be no electron cloud expansion. Nephelauxetic series. If various ligands are arranged in the increasing order of Nephelauxetic effect, the series obtained is called Nephelauxetic series. If different ligands are arranged in the increasing order of Nephelauxetic effect, the series obtained is called Nephelauxetic series. And the Nephelauxetic series of some common ligands is given here: F minus H2O NH3 oxalate ion ethylene diamine NCS minus Cl minus Cn minus Br minus and I minus. On moving from left to right, the electron cloud expansion effect, that is Nephelauxetic effect, increases. It has higher Nephelauxetic effect I minus, while F minus has lower Nephelauxetic effect. And as the Nephelauxetic effect increases, the value of beta decreases. It must be noted that the ligands having larger size has higher Nephelauxetic effect, while the ligands having a smaller size has lower Nephelauxetic effect. The value of beta, that is Nephelauxetic parameter, depends upon the nature of metal ion and also on the nature of ligands. The Nephelauxetic series given above is applicable to most of the metal ions. And it is obvious from the above series that the softer ligands, that is ligands having larger size, have a smaller Nephelauxetic parameter. The ligands which are softer, have larger size, have a smaller Nephelauxetic parameter beta, and a smaller the value of beta, greater will be the electron cloud expansion effect. It means the softer ligands having larger size have greater inter-electron cloud expansion effect, and the value of beta will be smaller. It can be explained as follows. The softer ligands such as Cn minus, CO, triphenylphosphine, ethylene, etc. contain larger atoms with vacant d atomic orbitals or vacant pi star molecular orbitals, which are suitable for back bonding. The softer ligands contain larger atoms with vacant d atomic orbitals or pi star MOs, which are vacant and suitable for back bonding. These d atomic orbitals or pi star MOs delocalize the metal electrons over a larger space. These d atomic orbitals or pi star MOs overlap with the d atomic orbital, forming larger molecular orbitals. Thus, the electrons of metal ion can move over a larger space, and hence they produce greater Nephelauxetic effect. That is, electron cloud expansion becomes more dominant. It can be represented with the help of diagram also. This is the bonding in the anion of gaseous salt. These four lobes, 1, 2, 3 and 4, are of vacant pi 2pz star molecular orbital of ethylene. These are the lobes of vacant pi to pz star molecular orbitals of ethylene, which overlap with filled dxz or dyz atomic orbital of platinum 2 plus ion in the anion of Jesse salt. This results in the formation of platinum 2 plus 2 ethylene pi bond or back bond. The electrons were originally present in the lobes of d atomic orbital, but on overlapping due to formation of this pi bond, the electrons of metal ion can move over a larger space. As a result, the distance between electrons increases and the interelectronic repulsion decreases, and it is nothing but electron cloud expansion effect. The d atomic orbital of metal ion overlaps with vacant pi star molecular orbital of ethylene, forming larger molecular orbital in which electrons can be delocalized over a larger space, resulting in increase in interelectronic distance and decrease in interelectronic repulsion. Thank you for watching the video with concentration.